So this section is on circular motion, and we're going to start with angle measures. So let's compare radians to degrees. I know you've had a look at them, but let's just remember that if you are starting on the initial side of an angle in standard form, and you spin it all the way around the unit circle and get back to where you started from, that angle is 360 degrees. And if you think of this as the unit circle where the radius is 1, the circumference of a circle is 2 pi times the radius. So 2 pi is once around the circle, which we already know. So 2 pi. So these are equivalent angles using different units. And then, so that's once around the circle. If we went halfway, that would be 180 degrees, and it would be equivalent to 1 pi, which we already know. So let's find a formula to convert between radians and degrees and radians. So let's write a proportion. And then we're going to remember the formula. So if I do radians over degrees, and I say that pi radians is equivalent to 180 degrees, now I have a proportion that's true. So if I solve this for radians, I'll have a formula for radians, and if I solve it for degrees, I'll have a formula for degrees. So if I solve it for radians, I would multiply both sides by degrees. So that would give me radians equals pi over 180 times the degrees. And if I solve this, that was a weird arrow. If I solve the same formula for degrees, I would cross multiply. I would get pi times degrees equals 180 times radians. And then one more step to isolate degrees. You can verify that this is true. I get degrees is equal to 180 over pi, so the reciprocal times radians. So these are angles that you probably know off the top of your head what they convert to, but let's just practice. So this is degrees. Let's say I want to translate it or convert it into radians. So I use my radian formula, and it would be equal to pi over 180 times the degrees, which is 60 degrees. And then you simplify, and 60 goes into 183 times. So this would be pi over 3, and hopefully we remember that pi over 3 is in fact 60 degrees. Now let's go the other way with a different angle. So pi over 6, and we want to convert it to degrees, so we use our degrees formula. So degrees is 180 over pi times the radians, so pi over 6. And the pi's cancel, and 180 divided by 6 is in fact 30 degrees. Hopefully that seems true to you. Fabulous. Let's remind ourselves of some vocabulary here. Coterminal angles are two angles that have the same terminal side. It doesn't mean they're necessarily the exact same angle. So in standard position means the initial side is along the x-axis horizontally to the right, and then you spin your angle around and you stop somewhere, and this is the terminal side. So two angles in standard position are coterminal if their sides coincide. I should say terminal sides. Sides coincide, meaning they're the same. So let's find some angles that are coterminal with 30 degrees. So let's draw a quick circle, and after this, we're just going to do it. We're not going to draw it. So 30 degrees is here. If I go all the way around the circle again so that I get an angle whose terminal side is here, but it's much bigger than 30 because I went 30 and then went all the way around, that would be 30 degrees plus 360 degrees. So that would be 390 degrees. That's coterminal with 30 degrees. We could find many of them, infinitely many. We can keep going around the circle. We could go 30 plus 2 times 360, and that would land us on the same terminal side. So that's 750 degrees, also coterminal. Or we could go the negative direction around the circle and land on the same terminal side. So that would be 30, and then negative is subtracting that number of degrees. So subtract 360, and that would be negative 330. Also coterminal. So 3 out of infinitely many that are coterminal. Let's do it with radians. Find angles that are coterminal with pi over 3. Which is 60 degrees, but we're going to stay in radians. So if we go all the way around the circle, we'll get to another coterminal side. So if we do pi over 3 and we add 2 pi, common denominator, that would be pi over 3 plus 6 pi over 3 equals 7 pi over 3. So there's one. We could add 2 pi, which is 6 pi over 3 again, to get another one, and that would be 13 pi over 3. Or if we wanted to, we could take pi over 3 and go the negative direction. So subtract 2 pi. So common denominator pi over 3 minus 6 pi over 3. So that would be negative 5 pi over 3. So again, 3 out of many, infinitely many coterminal angles with pi over 3. Another quick example, find an angle with a measure between 0 and 360. So we're staying in degrees. That's coterminal with the angle of measure 1290 degrees. So basically, we kind of want to unwrap this angle so we can find the angle that has the same terminal side that's less than 360. So if I take 1290 and subtract multiples of 360 until I get an angle that's between there. So the way I did that was I did quick multiplication, or like approximate multiplication in my head. So 360 is not going to be big enough. Twice that is 720. That's not big enough. So let's try 3 times that. So let's subtract 3 times 360 and see if we're there. So that would be 1290 minus 1080. So that's 210. So that is, in fact, between 0 and 360 degrees, so less than once around the circle. And it's going to be coterminal with that because we subtracted multiples of 360, meaning all the way around the circle. Now, let's quick remind ourselves of arc length, which you definitely did in geometry, and you probably did it again in algebra 2. So quick definition, if you have a circle and a central angle, meaning the angle has a vertex at the center, and this is the angle theta, that's the radius, then this little piece along the surface of the circle is the arc length. It's an arc, it's curved, and it has a length. So we're going to call that S. Remember, decided that it needed to be S for arc length. And again, R is the radius, and we need an angle theta, which I also forgot to write over here. So let's find a formula for that. So let's do proportion. Now, we have to decide if we're coming up with a formula from scratch. We have an angle in here. Is it going to be in radians or degrees? And then our formula will only work for that one. So we're going to do it in radians. You absolutely can find a formula that works for degrees. It will be different, but this is the one we're using. So don't forget, if you're using this formula and your angle is not in radians, you will get the wrong answer. All right, so let's make a proportion. So I'm going to do arc on the top and angle on the bottom. I'm setting up my blank proportion, and the left ratio is going to be my whole of the circle, and the right is going to be the part of the circle. So a whole arc would be all the way around the circle. So what's the circumference of a circle? It's 2 pi r, whatever the radius is. What's the angle if we go all the way around the circle? Well, once around is 2 pi. So this little part of the circle is going to be proportional. So what's that length on the surface? It's going to be S. And then what's the angle of the little part? Well, that's our special angle theta. So now you just 2 pi divided by 2 pi simplifies, and I want a formula for S, the arc length. So I would multiply by theta, and I would get S equals R theta. Isn't that fabulous? We've got a formula. So now we're going to use it. So first example. Oh, it's weird. So quick example, find the arc length of a circle with radius 10 meters that subtends a central angle of 30 degrees. That just means the angle swings through that size of angle. So we really just are plugging into the formula. So S is equal to R, which is 10, times the angle, which is 30 degrees. But remember, our formula has the angle in radians, so that is the wrong unit. So we could use our formula to convert from degrees to radians, but this is one of the special angles, so we know that that's pi over 6. Very important that this is in radians. And then if we wanted to get a number value to be like, how big is that really? So 10 times 3.14 divided by 6, and we get 5.236, and the units are meters because it's a length. All right, different question. A central angle theta in a circle with radius 4 is subtended by an arc of length 6 meters, and we want to find the angle theta. So let's use our same formula. So we know the arc length S is 6 and the radius is 4, and we don't know the angle. So it would be 6 divided by 4, which is 1.5 equals theta. So theta is 1.5 radians. And we didn't start with a value of pi, so there's not a pi written in there. But that is radians. Radians is this weird unit where it's the only unit that I know of in math where you don't actually have to say it. So you don't have to write down radians. But if you don't have a pi in the expression, it helps to keep track of what units you're using. All right, so that was arc length, and now we're going to do area of a sector. So again, here is my circle, and now we're talking area. So I'll use A for area of that sector. And then we also have the same central angle theta and a radius. So we're doing area rather than length of the arc. So let's do another proportion to find a formula for this. I'll set it up the same way. So I want area on the top and angle on the bottom, blank proportion, and the left one is going to be the whole, and the right one is going to be the part. So the area of a circle is pi r squared. The angle of go all the way around a circle is 2 pi. The part that we're interested in is the area, and the angle for that small sector is theta. The pi's cancel and the 2's don't. So if we solve that for area, we get 2a equals r squared theta. So that gives us area equals 1/2 r squared theta. So let's remember that and make sure you know that that angle is in radians. All right, quick example. We want to find the area, and we know the central angle and the radius. So area is equal to 1/2 the radius squared, which is 3 meters squared, times the angle. But that angle is in degrees, and I need it to be in radians. I know that one because it's a special angle, so it's pi over 3. I'm going to type that into my calculator and get 4.712. And it's an area, so those are square units. So the length units were meters, so the units are meters squared. All right, now we get to circular motion. So if you have something that's a circle that's turning, like a CD player, I know that's ancient times, but something that's a circle that's spinning, um, or a tire, or a Ferris wheel. So anything that's turning in a circle. So circular motion. Um, Here's some definitions. Angular speed is omega, and omega is the same omega that you see in the sine and cosine waves where the B used to be. So that's why I threw that in the last section. And it's defined to be the change in theta, so the change in the angle over change in time. And the time units could be minutes or seconds or various things. And then linear speed is something we've always known about. So speed is distance over time. So if we're talking circular motion, what's the surface of the circle doing? So that is the change in the arc length as the thing's spinning over the course of time. So those are definitions. So let's point out a few things that we already know. So we already know things about period. So the period of something that repeats. And so if we're going around in a circle, we start repeating when we get back to the place that we started. So the period of something going in circular motion is 2 pi over omega, which we already know. And we talked about frequency. So just a reminder that frequency is the reciprocal of period. So that would be omega over 2 pi. And then angular speed, let's talk about units for angular speed. So angular speed is going to be in radians because that's how we're measuring the angle over some kind of time units. And we have a formula that relates some of those same things. So S would be distance, radius, angle. This is not exactly this, but it's a formula that we can use to relate things. And then linear speed, like we just talked about, is distance over time. So the distance is S, and S, the arc length, is equal to r theta. So linear speed, V, for velocity, is also equal to r theta over t. So both of these things are true. Linear speed is arc length over time, so distance over time, but arc length is r theta, so it's also r theta over time. All right. Also want to point out that angular speed is not equal to frequency. They're related, but they're not the same. They have different units. Angular speed is measured in radians over time, and frequency is the number of cycles over time. So sometimes we want one and we have the other, so we have to be really careful about what kind of units we have. All right, so let's look at this example. So a boy is rotating a stone in a sling, the kind where you spin it around and throw it. So let me do a quick stick figure. Okay, so he's got the sling and there's a rock in the end and he's spinning it around in a circle over his head and then he's going to let go and whatever. But for now, it's spinning around in a circle. So this is something that's going in a circle. So now I'm going to do a top view of my circle. So his hand's in the middle. So the radius is 3 feet. And then it's spinning around. He's spinning it around. So we have 15 revolutions. So that's times around. So that would be cycles. Revolutions and cycles are the same every 10 seconds. So what's that? That's frequency, cycles over time. So that happens to be frequency. And instead of finding a formula, I'm going to do a unit conversion. Remember that from chemistry? So what are we trying to find? We want the angular speed and the linear speed or linear velocity. So let's find the angular speed. So we have something that's related but not exactly the same. So let's do a unit conversion to get it to be in radians over time, it's currently in cycles over time. So a unit conversion, remember a cycle is once around the circle. So um, once around the circle is 2 pi. So I want the cycles to cancel and I want to keep the seconds. So I can put cycles on the bottom. I want those units to cancel. And one cycle is the same as 2 pi radians, and that's a unit that you don't have to write, but I'm writing it so we know what we're talking about. So let's see what happens with our units. Those units cancel, and I'm left with 15 times 2 pi divided by 10 cycles. And so if you quick simplify that fraction, you get 3 pi, and it's radians, which is a unit you don't have to write, but I'm writing it, seconds. 3 pi radians per second. The angular speed, otherwise known as omega, is 3 pi radians per second. All right, we did that. So now we want the linear speed, so v. So let's use our formula. We don't have the change in the arc, although we could figure it out, but we do know r and theta. So this is going to be r times theta over time. That's the formula I want to use. Okay, so let's see what we know here. So we know that the units for angular speed are radians over time, and that would be theta over t. So angular speed is going to be radians per time, so theta over t. We already know that. So if I rewrite this as r times theta over t, so just a little bit of algebra here. We know the radius is 3 feet. And we know theta over t is omega, and that's 3 pi. So look what we just figured out. This is the same as r omega. So that's important. So let's write that up here. This is the same as r times omega. So we'll go back and point at that in a minute. So we worked this out. So we got 9 pi, lost a unit here, over seconds there. All right, so 9 pi feet per second, and that's not a unit that really helps. 9 pi, that's not a number that really helps us tell in our heads how fast it is. So 9 times 3.14. So that gives us 28.26 feet per second. That gives me a better sense of how fast that's going. So let's go back up here to linear speed. So linear speed equals change in arc length over time. It's also equal to radius times angle over time, which is also equal to r times omega. So 3 useful formulas up there, but always remember that theta is in radians. All right, I wrote this formula down here again. That's useful. And we've got another example here. This is our last example. So woman's riding a bicycle and she's got the diameter of the wheel here. So I'm going to write down the radius because that's always the number that's useful. So the radius of the wheel is 13 inches, and the wheels rotate at 125 revolutions per minute, and we want to find the speed. So this is, we're looking for a linear speed. So ultimately we want to find v. So let's do it the same way we did this one, but now that we've practiced, we're going to do it faster. So the other fact here, 125 revolutions, so that's cycles per minute. We have different time units. And that's not the units that I need in order to have omega. So I want my units to be in radians per time. So I will multiply by 1 cycle on the bottom and 2 pi on the top. So the cycles cancel. So that gives me 250 pi. The cycle's canceled, so I'm just left with minutes. It's radians per minute, but again, we don't need to keep radians. And those are the right units, radians per unit time for omega. So that's omega. So we found omega. And since we know that linear speed velocity is r times omega, so now we know the radius is 13 inches and omega is 250 pi per minute. And I simplify this and I'm done with the essence of the problem, except they were very specific about wanting us to have the units in miles per hour. So I'm not going to simplify it yet. I'm going to do unit conversions all the way over to here until I get the units I want. So I'm going to start with the time units. So I don't want minutes, I want hours. So I want minutes on the top and hours on the bottom. So there are 60 minutes in 1 hour. Remember this from chemistry? And so now I have the right units for time, hours, but I don't have the right distance units. So that's inches, and I'd rather have miles. So I don't know how many inches are in a mile, but I know how many feet are in inches are in a foot. So I want the inches to cancel. So denominator, so 12 inches in 1 foot. And then I know that there are 5,280 feet in 1 mile, and then the feet cancel, and I'm left with miles per hour, which is what I want. So now you multiply 13 times 250 times pi times 60 times 1, hit enter, and then divide by 12, and then hit enter again, or put parentheses and divide by 5,280. And you get 9.669, and our units ended up being miles over hours, which is what we wanted. So I do hope you noticed that we spent a lot of time working this one out and thinking and going back to the stuff that we knew. But now that we did it, these are the same kind of problem. We had the same kind of information. So we didn't work as hard the second time. We said, look, we got a formula here. We just need R times omega. So first, we put the cycles per minute and did a quick unit conversion to get it into radians per minute, so radians per time, and that's omega. As soon as we had omega, linear speed is R times omega, and the rest of it was unit conversions to get the right units.